The second part of this discussion deals with enthalpy from bond data. We can estimate this by looking at differences in bond enthalpy between products and reactants in chemical reactions. Essentially, bond enthalpy is energy required to break a chemical bond, so it is always positive. Bonds don't break spontaneously, energy is required, and then energy is released whenever new bonds are formed. So we can take a look at this and track it by saying that delta H reaction is equal to the sum of all bonds broken, energy required, minus the sum of all bonds formed, energy released. So that bonds broken relates to the reactants and bonds formed relates to products. This is kind of like looking at enthalpies of formation, and that we're looking at the difference between the energy stored in the bonds of the products and the reactants. However, in those cases, we're just looking at the difference in initial and final states. So we can often have those values being negative. You can release energy in a formation. Since bond enthalpy is a breaking of bonds, it is never, ever, ever going to be a negative value. So they'll always be positive, and they're always for elements in the gas state. And some other things that we need to know about them to make informed decisions is that they're estimates. They're averaged over several different elements, and they're usually used in organic chemistry. So there are a lot of compounds that have CH bonds where there are other things going on in the molecule that might influence the strength of those attractions for each other, but not to the extent that we might think. So you can get a pretty good value by averaging them. There'll be a few extreme circumstances, and those are taken care of in the tables of bond enthalpy data that are available. When we do standard enthalpies of formation, we're looking at energy released or gained in the making of each component. However, when we look at bond enthalpies, we're just looking at the difference between how much energy it takes to break all the bonds versus how much we can release when we put them all back together. So that if it takes more energy to break than is released when they form, we have an endothermic process, and vice versa. When we put in less energy to break them than we get released whenever they form their new products, then we have exothermic reactions. So here's a sample question. We're looking at the burning of methanol in oxygen to form CO2 and H2O. Notice these are all in the gas state. Like we said, bond enthalpy data is only relevant in the gas state. And we have a table of average bond energies in kilojoules per mole that's come from your textbook. So essentially the values in this table represent the energy needed to break or dissociate elements that are sharing electrons. First thing we need to do is balance our equation. So putting 3 halves in front of oxygen and 2 in front of water will balance. Also in bond enthalpy, we actually have to know what kinds of bonds are inside the compound so that we know how many we need to break and how many we need to form. So we'll have to draw structures for these things. It's not enough just to know it's CH3OH. We need to know how it's attached. And so this is what CH3OH looks like. It has 3 CH bonds, a CO bond, and 1 OH bond. O2 looks like this. It's 2 oxygen molecules connected with a double bond. And we have figured out in balancing our equation that we need 3 halves of a mole of this. So the values stated in the table are per mole. So if I have 1 OO bond, then I need to multiply that value by 3 halves. CO2, our first product, looks like this. It's 2 bonds where carbon is attached to oxygen by double bonds. And if you'll notice, this is a special case. CO2 has a stronger CO double bond than the CO double bond up here in the table found in other normal compounds like ketones and aldehydes and things of that nature. So we have this special value at the bottom that we use. Last but not least, we have H2O containing 2 OH bonds, and we have 2 moles of that, so we need to multiply 2 moles times the energy required for 2 OH bonds. And so first we'll look at our bonds broken. The bonds broken relate to the CH, the CO, and the OH from the methanol, and then the O2 double bond. So taking a look at those values, subbing in from the table, we can see that the energy required to break all the bonds in the system initially is 2,806.5 kilojoules. The bonds formed are related to the CO2 and H2O, so we've got 2 times that special value for CO2 at 799 and 4 times the value for OH at 467. Notice still all positive numbers. The energy that comes from the bonds being formed is 3,466 kilojoules. Now the way this is set up, I know when we did formation enthalpies, we did products minus reactants. Because of the definition of bond enthalpy, we do this backwards. We do reactants minus products, because the energy coming into the system goes to breaking the bonds and the reactants, and then when they form together to make new bonds, that energy is released, and so that's the negative sign convention for our energy. And so we take this, the bonds broken is 2,806.5 kilojoules, the bonds formed is 3,466 kilojoules. That's released by the bonds being formed, hence the negative sign, and we see that we release negative 659.5 kilojoules, which gels well with the idea of this being an exothermic combustion reaction. The last thing we want to do with this little segment is take a look at how reactions progress through their energy profiles through time. So we'll look at two different types, our exothermic and endothermic reactions, and identify some key points and some things that make them different from each other. The first graph you're looking at shows what happens to energy through a reaction. Energy comes in, is stable, then it spikes, drops rather rapidly, and levels out again. That initial level spot represents our reactants. This is where the system is in the beginning. The ending at the bottom where it's level again represents the products. This is before a reaction, this is after a reaction. And so we have some key identifying features we need to look at. The first mark here shows where or what happens between where my reactants are through the spike and back down to where they are again. And the last little spot we want to zero in on here just is to know what the difference between the reactants and products is. The nice little hump that you see at the beginning is called the activation energy. This is the energy required to get a reaction started or to reach the activated complex. The bigger the value of this number, the bigger the hill that we have to climb before we can do the reaction, the less spontaneous or less favorable the reaction is. Something else you need to note is that while this energy does come into the system, it's paid back out, so it will not be included in the difference between my initial starting state and my final state. So this is part of the reason that we define our state functions as path independent. This energy can come into the system, even though it's going to come back out. It's not going to be accounted for in my state function, which is enthalpy, which is shown here, just the difference between the reactants and the products. But again, we can have a reaction that's very exothermic like this, which this happens to be an exothermic reaction. We can release an awful lot of energy, but if we have to climb too high of a hill to get started, it's not going to happen. The next pathway we want to look at looks like this. It shows my reactants at very low energy and my products at very high energy. So this is going to be a case where we have absorbed energy into the system in the form of chemical potential. Our reactants have stored it in their bonds, and so here we have our line demarcating where the energy of the reactants is. Notice the extreme height of the activation energy. Reactions like this are very hard to get started. They require a lot more push to get going. So they have to get all the way up over this hill, and then when they get over the hill, they don't pay it all back out. The delta H then moves from low energy to high energy. So this is a positive delta H. This is endothermic. We have taken energy in and made less stable products, at least thermodynamically stable. And so this is a hallmark of an endothermic process. Doesn't mean that it can't happen spontaneously. As we start our next segment where we talk about entropy, we'll talk about the interplay of these two things. But at least from the standpoint of heat energy coming into and out of a system, this would not be a favorable reaction.